scatter plot, so I'm plotting one against the other. What I would like to focus on right now is the residuals. So I already told you that the residuals come from the data. Let me see. I want this 1%.
Yeah, now yeah.
That's better?
A little bit more.
Okay. Now look at this. These are the residuals. They have the same size as your data. So there's 201 emissions and 61 excitations, etc. Now that means that I can plot them just like the raw data, and that's what is done down here. Here I'm looking at the residuals for sample 1, sample 2, 3, 4, 5, etc. So this is really nice for seeing if there's structure left in the data, and indeed there is, because we have this Rayleigh scattering. Now this is what is called a normal probability plot. That's all the residuals. If they were random and Gaussian, etc., it would be a straight line. So this indicates that there's structure left in the data, and there is. Now I can also, for example, I can take all these and take the sum of squares of these. That will show me how much residual variation is in sample 1, and 2, and 3, and 4, and 5. And if I do that, I get these numbers. So here I can check for outliers. And if you are used to doing two-way analysis, you are also used to using a plot where you show the residuals versus the whole tellings t-squared or the leverage. That's a standard plot for finding outliers in chemometric models. And we have that available here as well. Now, just one thing I want to show you here is that we can also take all of these, all the residuals, and we calculate the residual variance. We take all the residuals and square them, add them together. If I do that, let me make that a little smaller, and I divide by the sum of squares of this, that tells me the fraction of unexplained variation. So this is the fraction of explained variation. So this is how much variance is explained in percentages. So it's the size of the residuals relative to the size of the data. And that's the number that you see up here. That's how it's calculated technically. So this model explains 99.937% of the variation. So remember that we have the variance explained up here. That's going to be important shortly. And it's just the size of the residuals, basically. Okay. There's one more thing I need to explain about the strangeness of Parafac. Imagine that we're doing PCA, and this component explains 60% of the variance, and this one explains 30%. How much variance do these two components describe together if it's PCA? Well, they explain 90%. That's very natural, we think. But let's do Parafac, and let's make it complicated. So let's say that this one is explaining 60, and this one is explaining 50. How much are they describing together? Not 110. That's not possible. But this is a basic result from statistics, and we don't remember it. But you cannot add variances together. You can only do that if they're independent. That's the only situation where you can add variances. And in PCA, they are independent because they're forced to be orthogonal. So that's very lucky for us, because then we can just add them. In Parafac, we don't want orthogonal loadings. I want pure spectra, and they are not orthogonal. So I don't want orthogonal components, and therefore I cannot add variances. They simply don't add. There's no way you can add Parafac variances. And they can go beyond 100, but it makes no sense because you cannot add them. So together, if I want to find out how much do they describe together, I have to look at the combined model of both of them. Wow. Like this. And maybe that will explain 80%. So I have to look at both of them together. This is really annoying, and I apologize, but that's what happens when you do Parafac. So you cannot add the components. You can look at the total variance, or you can look at the individual variances, but they don't add to the total. If I really wanted, what I could do is that I could say, hey, how much of this is unrelated to that one? So I can look at the unique variance here, and the unique variance here. But it also doesn't add up. It's just another number. And I'm sorry I have to make life so complicated here. But these are the numbers we see here. So this is the variance of component 1, component 2, and component 3. And they don't add up. So I can just look at them. But I also plotted the unique variance. And you can see they're very similar, which is often the case, but it doesn't have to be. And the red one is smaller than the other one. Now the reason I'm telling you about this is that we're going to use it shortly when we have to discuss the two biggest problems with Parafac that you have to be aware of. So remember that we cannot add variances, unfortunately. Where were we? Okay. So I told you that when you push the button to get Parafac, then maybe you're not going to get it. If the data are nice, like these fluorescence data, it's no problem. I'm going to get the same solution every time. But every now and then you will run into problems where you're not going to find the solution. And there are two problems. And you need to know that they exist if you really want to do nice Parafac models. It's not a big problem, but you need to know. One is that it may not converge to the solution. And the other one is a really weird one. This is actually why the mathematicians hate Parafac. It is that something called two-factor degeneracy can occur. And I'll explain what that is. But it's a situation where Parafac simply refuses to work. Okay, so let's start with the convergence. So remember that when I try to model Parafac, I'm guessing A, B, C, A, B, C. I'm improving A, B, C, A, B, C, A, B, C to make the residuals smaller and smaller and smaller and smaller and smaller. That's how it works. Now when you do optimization like that, here we have the sum squared residuals. So I'm guessing my parameters. I don't have only one parameter, I have many, but now I'm plotting just one. I'm guessing, and I want to end up here. But the problem is, if I come to a local minimum like this, Parafac is going to stop and say, hey, I found the solution. So we can have local minima, because the Parafac problem is non-linear. So we cannot guarantee that we're going to get the real solution. And these ones are not solutions. It's a local minimum. It has nothing to do with the solutions. You have to get this one. And that's a problem. And I'll show you an example. Let's see if I can find it. Oops. We'll use a data set that is a little bit more complicated. Because it's really difficult to have problems with, oops. with this small data set. So now I want to use a more real one. And just a minute, I have to find it. I'm sorry. 12 seconds and then I have it. It's gonna be a sugar data set, so that's always nice. Just want to see. Here we are. There we are. Yes, got it. Okay. So, let me clear my workspace and say load sugar. So what I have here is a fluorescence data set of samples taken from a sugar factory. So this is actually white sugar taken from the last centrifugation of a sugar factory every 8 hours. So in Denmark, the sugar campaign is 3 months. So every 8 hours for 3 months, we took a sample of sugar out, dissolved in water, and measured the fluorescence. So we have 268 fluorescence landscape. And we want to understand the process dynamics and maybe predict some parameters. We only measured at 44 emissions and 7 excitations. This is long ago. This is actually 20 years ago. Let me make a little movie of sugar production from a fluorescence perspective. We do this. I'm just going to plot all the data. Okay. So these are the 270 samples. They look really boring, but that's how the fluorescence look. Would be nice to have a better resolution, but that's okay. Now what I'm going to do is that I'm going to fit a 4-component. See, in the end this comes up because the sugar is really dirty in the last few weeks, with the last week basically. Okay. So I'm going to fit a Parafac model with 4 components. And okay. Now I actually know that 4 components is not the right number, but I'm going to do it anyway. Look at this. It says 99.919% variance explained. Just a number. Let me do it again. Okay, it says the same thing. Let me do it again. This can be a very boring 1 hour from now on. Okay. But don't worry, it's going to come. Here we are. Thank you. Very good. So you see now, I fit a 4-component model. And I don't get the same solution. I get this one multiple times, and I get this one multiple times. And that's really annoying. They cannot both be a solution, because they should be the same. So this is a local minimum. This one is a local minimum, because this one works better. So there's no way this can be a solution when there's a better fit, because Parafac is defined as the best fit. This is a local minimum. And that's a problem, right? Now the real problem here is that I use too many components. So it's not a real problem. If I use the right number of components, I'm not going to see that for this data set. But it's still very annoying, because now when you push the button, you're not actually sure that what it's giving you is the right solution. So we have to be able to deal with that. And how you deal with that depends a little bit on the scenario. If you want to be really safe, you could fit Parafac 20 times every time. Every time you fit a Parafac model, you just fit it 20 times and you take the best one, for example. Now, if you had a lot of computer power, that's a nice thing to do. But I don't have time for that, so I never do that. So what I do is that I don't care, and I only investigate local minima if I see something that's problematic, if I see something that's strange. But if you really want to make it sort of, let's say, user-friendly, you really should look into this and handle this. So you could build some kind of intelligence around it if you were a software company or an instrument company and you want to make it automatic for the user. You should probably run Parafac. Maybe you have a GPU on your computer, so you can run 20 models at the same time, and then just let the user know that, hey, there is a problem, or maybe there was a problem, but I fixed it and took the real solution, something like that. I never do that because I work manually with my model, so I just check if I find strange solutions, whether I have local minima. But for 95% of the time, I don't even think about it. Because the good models tend to not have this problem. It's only the bad models or the difficult models. Now, I want to fit the model a few more times because I need to find, there's a third local minima I know. And I want to find that one as well. And it's not this one. That's the hardest one to get. Wait a minute, I will do this. Okay, so now I'm just going to fit 10 models because I want to find one other one. This is the global minimum. This is really exciting. This is the local minimum. And I think it's in between. There's another solution in between these two, and it has some very interesting features. Please. Well, okay, maybe I will leave it calculating, and then I will show you what the interesting features are. Stop.
Rasmus, is it okay to ask something?
It's more than okay.
Yeah, so when, so these local minima and so on, is there a way to plot, to visualize this? Is it like a landscape, or what is it, 3D, or how?
Let me show you. So that's a good question. So when you do your Parafac model, let's say I'm estimating a one-component Parafac model. And let's say it's this. Let's say it's the fluorescence data. I'm trying to find a one-component Parafac model. I have 201 emission parameters, 61 excitation, and 5 sample. So that's 262, 267. So I have 267 parameters that Parafac has to estimate. And that means that the sum squared residuals that I'm trying to minimize lives in a 267 dimensional space. Because it's a function of all of these, and I'm trying to optimize all of them. So it's impossible to visualize the actual space. This is a general problem in optimization. It's not specific to Parafac. There are some methods, there are some fields like global optimization that try to fix the problem, but there is no fix. I mean, there's no real fix. But you can handle it more or less intelligently. And the main thing is you have to know that the problem exists, first of all. Ah, I got it. Thank you. Then we can stop. Okay. Did that not go? No, PowerPoint. Okay, so this is one problem, the convergence. The other problem is this two-factor degeneracy. And I'm sorry, now it gets really mathematical. Not too bad, but two-factor degeneracy means that you have two components, like this, but they are exactly the same with opposite sign. And that means that the sum of these two is 0. They don't do anything, but they appear. It has nothing to do with your data, it's a mathematical artifact. So let's say I'm doing a two-component model and I get these two. That means a two-component model does not exist for these data. So there are certain Parafac models that do not exist. Again, this is very annoying. In PCA, I can say I want a 17-component model and I can always find it. In Parafac, some of them don't exist. And that's weird stuff. If you really want to fix it, you can go to complex numbers because then it exists if you take the imaginary part, but we don't want that. Okay, now when this happens in your data, you have to fix it somehow, and I'll tell you the different ways of fixing it. But the first thing is that you have to be aware of how to detect it, what it looks like, and that it doesn't mean your data are behaving like that. It's Parafac that's not behaving. So here's an example of a two-factor degeneracy. Look, these two emission loading, well, it's not emission. These two loadings are almost the same shape. These are the same shape. These are the same shape, but opposite. So this product, if you take the two, the sum of them becomes 0. And if you're really interested in this, what is kind of fascinating is that the more you iterate, the bigger these two become. They grow towards infinity, and the similarity grows towards 0. So asymptotically, they will become 0 in the sum and have infinite size. And it's really all just weird stuff. Before I tell you how we can fix it, let's take a look at this third local minimum that we have in this data set. And that's this one. So this one has a different fit value, and we find it repeatedly.